Hey everybody, we're going to talk today about the torque that you get when you have a loop of wire in a uniform magnetic field. And this is really an important subject because this is kind of the foundations of how electric motors work, and our society wouldn't be where it is today without electric motors. So let's go ahead and get started. First, I'd like to review electric fields and magnetic fields. And we'll see how they're very similar and how they're similar. And then, oh, excuse me. Then we're going to talk about the torque on a loop, torque on a loop. And the equation we're going to eventually derive here is the torque on a loop of wire is going to be the current in the wire times the area crossed with the magnetic field. Okay? So this is our target right here. And we're also going to find, we're going to define this thing called the magnetic dipole moment. Or just the magnetic moment. Magnetic dipole moment. Okay, and that has a symbol that, well, I'm sorry, it's mu, but it's mu with a vector hat on it. When you see mu with a vector hat on it, it usually means the magnetic dipole moment. And by definition, it is I times A. Now, I'm putting a vector hat on an area, which we've done before, right? And we're going to define the direction of the area on a loop here in just a moment. So let's talk about electric fields real quick. An electric field if I have an electric field, what does that mean? Well, that means is anytime you have a force field, it means that a force is going to be applied to an object because of a certain characteristic it has. A gravitational field applies force to objects because they have mass. Electric fields apply forces to objects because they have a net charge. And we have the equation for that is, F equals Q times E, where this is the electric field. Okay, this kind of defines what an electric field is. What do electric fields do? They apply forces to objects that have a charge on them. Magnetic fields. Now, nature turned out to be not very easy for us to understand, and sorry, that's just the way it is. But and magnetic fields are kind of tricky. You have to get used to them. Magnetic fields apply forces to objects because they have a charge and because they have velocity. If an object doesn't have any velocity, there won't be any force on it. And the equation that describes that force, F, turns out to be QV cross B. Okay, and or QVB times the sine of the angle between V and B. So there's that angle theta right there. And then you use the right-hand rule for cross products to figure out the direction of it. Okay, so if I go V cross B, I'm going to go into the paper here. And into the paper, well, let's make this I hat, J hat, and K hat coming out of the board. And so, so this right-hand rule, this will be in the QVB sine theta in the K hat, negative K hat direction, right? Negative K hat, because V cross B, my thumb's going to be pointing down into the paper. So that's what magnetic fields are. They're just a region of space where if a charged particle is moving, it'll feel a force that obeys this equation. Now, there is a connection between electric fields and magnetic fields. And that's why we call it the electromagnetic field. And that will come later in your physics education. But for right now, we can treat them as separate things. And in fact, that's what physicists did when they were first exploring electric fields and magnetic fields. They thought they were completely separate. And then a guy named James Clerk Maxwell figured out that they were really interrelated. So we'll talk about that later. Now let's talk about a loop of current. What do we mean by a current loop? Well, a current loop is just we'll make it a rectangle today. It doesn't have to be a rectangle. That's got current running through it. Okay, so let's just have current running like this. And it's just charge circulating through like that. Well, obviously something has to be driving this current. Somewhere in there you must have a little battery or something. And, of course, all wires have a little bit of resistance, and it makes this current. You can figure it out with using Ohm's law and all that. And what we just do in this analysis is that we just ignore it. We just say, don't even bother drawing the battery. Just do that. Now, this current loop has an area like this. Okay, so it has some area, and we're going to use that area. But we can define the vector of this area this way. It's going to be equal to A. Well, A is just the magnitude of the area. If you make this A times B, that's what we're going to end up doing. A times, it would just be, little a times b, that would be my area. But what's the direction of the area vector? Well, remember with Gauss's law, we said the direction of the area vector was outward from the Gaussian surface. We just arbitrarily decided to do that if you have a enclosed volume, that the area that encloses that volume, the area vector always points outwards away from the volume. Well, we have to come up with a similar way of doing things here, and what we're going to do is this. Okay, and this might bug some of you, but I'm sorry. We're going to define it that if you take your right hand, let me zoom all the way out here and even lower the camera a little bit. So my area is going counterclockwise like this. You take your right hand and you circulate it in the direction of the current, and your thumb will point in the direction of our area vector. So again, we use a right-hand rule, but for currents to define the area. So in my little drawing like this, if I draw it in perspective, and lower down and zoom back in, this is my area vector. And if I make, again, this is I hat, and, oh dear. Well, anyway, we'll do the I hat, J hat things anyway. But anyway, it's the area, and then use the right-hand rule to figure out the direction of that area vector. And the right-hand rule is you circulate your fingers in the direction of the current. It just, we needed a way to say, well, because we could have put the area down here, right? But no, we're not going to do that. So there you go. There's a current carrying loop. Now what we're going to do is we're going to look at loops in current and constant uniform magnetic fields. Okay, so let's do one like this. Let's imagine a loop. Let's imagine a magnetic field. It looks like this. Am I on camera? No, not quite. All right. Hey, I bothered to check. So here's a magnetic field. It's going into the piece of paper, and it's uniform. And I'm going to put a loop in like this. And again, my loop has a height of A and a width of B. And what I'm going to do is I'm going to circulate a current like it was before. There's I. Now, what I can do is look at each branch of this, and I can use the force equation for the well, I'm going to use the F equals IL cross B. Right? We derived that last time, sort of. And, well, here, let's take a look at this wire right here. Okay. Well, it's got a current of I. So what is the force on this part of the wire? Because, look, you got a current. It's in a magnetic field. The wire's going to feel a force. So it's going down like that, right? Okay, so the force is going to be, well, for this one, let's just draw it right over here. On this side, it's going to be, well, I. Now, what is L? L is this length right here, which turns out to be A. And then we know B. Now we can use the right-hand rule to figure out the direction. And here's what you do. You go I cross B. So you go, you know, this cross this. It's going to be out like that. Okay. Right. Did I do that right? Oh, wait. Did I use the wrong hand? Here's I. No, I used my left finger. That's why I screwed it up. Okay. So if this is going like this, I'm going to feel a force inwards, like this. It's going to try to push it in, not like that. Okay, it's going to be a force inward using the right-hand rule. So take your right hand in the direction of L, cross down to B. My thumb will point in that direction. Now let's take a look at this wire. Well, this has the force over here is equal to I. Now what is L in this case? Oh, it's B. And then times big B. And then if I go I cross B, my thumb goes up. Oh, look at that force. And then look at this over here. The current's going up. So I cross B goes inwards like this. Of course, IAB, it's going to be IAB, right? F equals IAB. And then this is going to be F equals I, and the length is B, little b, times B, and the direction I cross B is going to be down. And look what happens. All these forces cancel each other out. There's no net force on this loop of wire in this magnetic field. There's no torque either. Okay? So now this is going to be important. This is going to be important here in a minute. So let's... So what we can say is that, now let's take a look at the area vector here, by the way. Look, here's the area vector, it comes out. Look at that, there's the area vector. So the area vector is coming out towards your eye. The magnetic field is going down, and there's no torque. All right. Now, let's take a look. What if we have the magnetic field laid down like this? Okay. Let me zoom out a little bit. So what if it's laid down like this? Okay. So here's my same current carrying loop. It's got a height of A and width of B and so on. And let's have the current we'll just keep circulating it like that. Now, this is different. Just changing the orientation of this loop within the magnetic field, I get something different. I have, well, let's see. Let's take a look at this wire right here. What's the force on it? F equals, well, the length, it's I times the length of the wire. It's A times B. Now, what's the direction? Use the right-hand rule. I is going down. I is going down. Cross over to B. Try to do it. Let's see. I going down. Cross over to B. My thumb is pointing up. Boom. There's my force pointing up. Okay. Now let's do this wire. Well, you could try this. F equals I B times B, but okay, what's going on here? Can you tell me why? What's going to happen? Well, look, it's L cross B, but the current, the direction that the current is flowing, and the magnetic field are parallel. So when you go sine theta, you have sine of 0 degrees, but that's 0, folks. There's no force. F equals 0. That's different than our other loop. Now, if I come up here, I get the same equation. F equals IA times B. But look, what's the direction? Well, the current's going up. So current going up, cross over to B. My thumb isn't down into the paper. So I get a force that's down like this. And then, of course, up here, the force on this line segment, because of the cross product, is 0 again. Now look at this. Over here, I had a force on all of the wires, but they were all canceling each other out. Over here, I have two forces. They cancel each other out in terms of direction. They're equal and opposite in direction, but look, they apply a torque. Now let's imagine that this is our center line right here. And I'm going to figure out, so, I think that this loop is going to try to rotate like this, isn't it? Under the influence of these forces. And so what is the torque on this wire? Well, it's the torque due to this. Well, torque equals R cross F. Do you remember that? I hope so. So the torque due to this force, what is R? Start with R. R is from here, from the axis of rotation to the application of the force. What is it? It's B over 2. Okay, and then what's the force? IAB. Okay, and this is trying to make it rotate in this direction. We'll call that a J-hat direction. Okay, because we'll make this direction J-hat. We'll make this I-hat, and then coming out of the paper is K-hat. Okay, now, plus, plus the torque due to this force. Well, what is it? Well, look, it's B over 2. This is B. So this is B over 2. So this is B over 2 times AB. And look, it's trying to make it rotate this way, so, it's J hat. So the torque is equal to, B over 2 plus B over 2 is just B. So it's A times B times big B in the J-hat direction. Now, do you see anything neat here? This is cool. Look at A times B. What is A times B? A times B. It's the area of our loop. So I can say that the torque here is equal to IAB in the J-hat direction. Voila. Now, we have to get a little bit complicated because, look, over here, let me zoom all the way out. Over here, when the loop was oriented in this way compared to the magnetic field, we had no torque at all. And over here, when the loop is in the plane of the magnetic field like this, well, I got a lot of torque. Well, what about somewhere in between? What if I took this loop right here and I rotate? Well, it's trying to rotate like this, isn't it? It's trying to rotate like this. So what if it's oriented like this at some angle instead? What's going on? Okay, well, what I'm going to do is draw a little picture in cross-section of this. Now, what I have to do now is this, and it's kind of, it'll be, well, it makes it kind of difficult. I'm going to look at this edge on, okay? And what I'm going to do is this. I'm going to show the, here's my magnetic field. Let's just show it like this, okay? And when this thing was all laid out like in this orientation, what I'm going to do is I'm going to rotate it. I'm going to kind of rotate it like this so that the current, here's the loop, and here's this loop now. I'm sorry. Here's this loop, and I'm going to take a look at this loop, and I'm going to rotate my view of the loop so it looks like this. So because this current is going down, if I rotate the bottom of this up, now the current is coming out at us, okay? And then it comes out at us, and then it runs along like this, and then it goes in on this side. Okay, so pause the video if you don't understand this and think about it. It is explained in your book as well. Now when I do this, I still get the same idea. I get I cross B. If I rotate this up like this force gets rotated from coming at you. It's going to be up like this, right? And then this is the force. And so this was B over 2. This was B over 2 from here to here, from here to here. And here's your torque. This was, this force, right, was B over 2 I. Oh, I'm sorry, that was the torque. The force was I AB, and this force was IAB as well. And then we added, the torque of this, and we added it up to get that total torque. Okay, so this was the situation that we drew, and I just redrew it a little bit, looking at it edge on instead of over the top. Here, so let's now. What if this thing got rotated a little bit? What if I took this and I rotated it at some arbitrary angle, like this? Okay, and well, oh, let's take a look at our area vectors too. By the way, in this one as well. The area vector here is still coming out of the paper, right? So here's my area vector. Because if I circulate my hands in the direction, like my area vector is out like this. Well, if I do this, look what's happening. The current is coming out of the paper here and then back down on the other side. So my thumb is going to point. So here's my area vector. Now this is going to be really important to our analysis here. So here's B. Here's the direction of our B field. Here's my area. Well, if I rotate this up, look, this is going to apply a torque, and it's going to rotate it up like that. So let's take a look at it. Here's my current, like this. Now, the force of I cross over to B is still straight up. So here we have I, A, B like this, and then this is straight down like this. This is I, A, B. Okay, so there's our forces. But take a look. The torque has changed here. See here, this used to be B over 2. But if I rotated this by, and this is the angle, here's our area vector. If I rotated this by theta, okay, if I was here, and then I rotated this by theta, then I think you can see that, yeah, let's see, hold on, that this is theta up here. Does that make sense? And yeah, that's right. So think about this. If look at our A. If A well, I'm just gonna move on. I'm just gonna say this is the same as this. Okay. Now, if this is B over 2, this is our hypotenuse, This is B over 2 sine theta. So this is really our lever arm. So the torque here from this guy, the torque from this force is going to be B over 2 sine theta. That's my R crossed with I, or it's crossed with my force. And then plus from the other one. This other one's going to have the same torque. B over 2 times sine theta. Oh, my off camera, no. This is going to be IAB. And so what we get is our torque is equal to, same thing we had before, IAB times B, but now we've got a sine. IA little b times big B times the sine of the angle. And this, well, and here's A. Well, look at this. Look, A is a vector. That's the area vector. B is a vector. And I'm multiplying by the sine theta. Well, that's a cross product. That defines a cross product. And so we get the torque is equal to IA cross B. And this defines the torque. This defines the torque that I get on a loop in a wire. And look, it works for this. Let's go back way over here to this one. What's the angle between my area vector, here it's coming out of the board, and the magnetic field is into the board? Well, that angle is 180 degrees. Well, when you go IAB sine theta, well, the sine of 180 degrees is 0. So there's no torque. So this gives me an equation now for the torque of the torque on a loop of wire in a magnetic field. Now this is messy, and I'm sorry. Every time I've explained this, it gets messy, and it's not one of those easy things to explain. And you should read the book. You should watch other YouTube videos. You should, you spend a lot of time thinking about why this is true. Now, we have a name for, if I have a loop with current in it, it turns out to be very convenient to just multiply, well, we just said torque equals IA cross B. Well, think about this. We're talking about steady currents. We're not going to change the current, and the loop isn't going to change shape. We're not going to do that. I mean, think about a motor. Does a motor change its shape? Does it change its cross-sectional area with time? No. And we usually try to, well, let's deal with direct, with DC, motors. The current is the same. So they don't change in time. And so we're going to call this guy right here, it's a characteristic of the circuit. It's a characteristic of our device. And so we give it a name. IA, by definition, okay, is called the magnetic dipole moment. Okay, and the symbol we use for a magnetic dipole moment is mu, with a vector on it. Sorry. It's, yeah, I know, mu. What have we used mu for so far? Well, coefficients of friction. But when you see mu with a vector out on it, that's not a coefficient of friction anymore. It usually means a magnetic dipole moment. You have to look at the context. So we can say that the torque is equal to mu cross B. And that is something that you will see. And that's it.